Hello everyone, I'm Amir shayan moghaddam. In this video I'm going to talk about how to simulate vacuum cleaner robots navigation in MATLAB Simulink by using Simscape blocks. As you can see, in this video I'm going to talk about 3D model of vacuum cleaner robot and how to import it to MATLAB. What is Simscape and which blocks were used? Simulink blocks and subsystems in this project. 3D word editor. And at the end of this video, I will run the project and we will see the results that I've been looking for. In this kind of project, there are two ways to import the model to MATLAB. First is using solid block in Simscape that you can add to your project from library and use different joins to relate different parts of the model. Second way is using SolidWorks. You can design or create your own model or get model from engineering communities and use Simscape multi-body link, which is a relation between SolidWorks and MATLAB. And by using that, you can export more model from SolidWorks, and with writing this code smimport model name.xml in command window, you can import your model to MATLAB. For this project, I chose the second way. For doing that, I used STP file of vacuum cleaner robot that was gotten from the GrabCAD, which is one of the best community for uploading and downloading CAD files for different projects. For using this model in simulation, first it has to be prepared for importing to MATLAB. For doing this, every part which create wheels should be an assembly part, and other parts should be another assembly parts. After that, we have two assembly parts for wheels, just like this, and one assembly part for a body. For both wheels, a specific coordinate system should be defined, like this. And for doing that, you could use coordinate system in reference geometry in assembly section. After that, mates or constraints should be added between body and each wheels. For this project, concentric and coincident are enough. If we click on concentric and go to edit feature, you will see lock rotation checkbox. Let it be checked like this, because if you check this box, the wheels won't rotate respect to the body. After that, your model is ready for importing to MATLAB. And for importing to MATLAB, first you have to export it from SolidWorks. Click on Tools, Simscape multi-body link, and export wherever you want. And after that, as I explained at the beginning of this section, you could write a code in a command window in MATLAB and import your model to MATLAB Simulink. In this section, I'm going to talk about what is Simscape and which blocks were used. Simscape enables you to rapidly create models of physical systems within the Simulink environment. It has 6 categories: driveline, electrical, fluids, foundation library, multibody, utilities. I used multibody blocks in my project. Now I'm gonna explain every multibody blocks that I use in this project. First, I'm gonna start with word frame, which creates a fixed coordinate system. And if you double click on it, there is only description and nothing can be changed. After that, the next block is mechanism configuration, where I added gravity to my simulation. And the third one which is very important, is solver configuration. For these kind of projects, the default values are good, but if the equation for us harder, we should change them to get better results. Next block is revolute joint that can be added from library, or if you properly import 3D model and add rotation between wheels and body, this block would be added without using library. This block represents rotational relation between base and follower, and also you can get values of velocity and position of follower respect to the base. For this project, I got velocity of wheel respect to body for giving a specific torque in revolute joint actuation section. I put torque on automatically computed and motion provided by input. The next block is planar joint, which has 1 rotational degree of freedom and 2 transitional degree of freedom. For this project, I needed exact location of robot respect to the world, and after location calculator subsystem, which outputs were location of body respect to x and y axis, and rotational value respect to z axis. In planar joint, in px, py, and rz, in actuation section, I chose provided by input for their motion, and planar joint get position value from its input port. Next block is transform sensor, which gives us transformation value of follower respect to the base. In sensor subsystem, I use 2 transform sensors, one for rotation and the other one for position of robot respect to the world. The next block is rigid transform block. Rigid transform block was used to transform follower respect to the base. After that, there are 2 blocks that are very important in simulation when we use Simscape block in our project. Those are Simulink to physical converter and physical to Simulink converter, which connect Simulink blocks to Simscape blocks. For showing accuracy of my robot algorithms, I use 3D World Editor to create a room consist of a wall and furniture, like bed, dresser, desk, and chair. And I use library of MATLAB to add this component to my room. If you want to rotate items in 3D World Editor, you should change values in SF rotation. What is SF rotation? SF rotation represents a vector of 4 floating point values you use for specifying rotation coordinates of an axis plus rotation angles around that axis. If you click on rotation, you will see 4 places. The 4th place is for rotation angle, and the others are for choosing axis that you want the item rotate respect to that. After that, I had to import robot to this room, and for turning STP model to VRML file in SolidWorks, I saved the file as .wrl, and in option I chose VRML 97 for its version, because the 3D World Editor only accepts this version. After that, I opened the file in 3D World Editor. Then I selected the parts which were blind to wheels and grouped them, and for body, the remaining parts were grouped. For importing robot, you should open robot in 3D World Editor, then add room as an inline. Click on Nodes, Inline Virtual Reality File, then open the rooms. After that, the robot and room are ready for our simulation. In this section, I'm going to explain blocks and subsystems that I use in my project. First, I'm going to start with wheel subsystem. In wheel subsystem, as I explained before, I use revolute joint. In revolute joint, in actuation section, I chose provide by input for motion, and revolute joint get angular position as an input, and I use PS integrator because the wheels could rotate at constant rate if we use PS integrator. Next subsystem is location calculator for calculating robot translation. There are some formulas for a robot to get position and angle values by means of velocity of its wheel. By knowing velocity of left wheel and right wheel, we can calculate velocity of a robot. And also, we can calculate the distance between center of robot and instantaneous center of curvature, as I named it W. And with this formula, we can calculate Px, Py, and theta. And I created those formula in this subsystem to get Px, Py, and theta, and give this value as an input to our planar joint to make a relation between body and a robot. After location calculator subsystem, I'm going to talk about sensor subsystem. First, I'm going to explain my ideas and the sensor that I've used in my project. In this project, I used 6 ultrasonic sensors, and at the beginning of this project, I had idea to create ultrasonic sensor with Simscape blocks, but due to lack of information about it on internet, I reached to using virtual sensor idea. In this idea, I wrote a code in MATLAB function to find the location of each sensor every second in simulation, and to check if there's an item in front of each sensor. I wrote a formula to add specific ranges to each sensor position, and check that new position with binary lookup table that I've created from my 3D room. After that, if there was an item, output of my lookup table would be 1, and if there wasn't, output would be 0. In a sensor matrix, and comparison between measured value and ranges for each sensor helped us with our chart. Now I'm going to explain every blocks in this subsystem. In this subsystem, to distinguish between rotation sensor and position sensor, I use 2 transfer sensors, one for rotation value and the other one for position value of robot with respect to the world. After that, I use PS Simulink converter to be able to connect physical port of transfer sensor and Simulink port of MATLAB function. After that, I used rotation matrix and X and Y position as an input to my MATLAB function. In my MATLAB function, first I used this formula to find angle of robot from rotational matrix. After that, in my MATLAB function, I wrote some code to find location of each sensor and also prepare code for giving X and Y position to my lookup table. I created lookup table by using some for loops. After lookup table, I use another MATLAB function. In this MATLAB function, I use this trick that if there is an item, lookup table gives us 1. Then I subtracted it from 1 and multiply it to my range. So if there wasn't any object, Sensor subsystem return exactly value of ranges, otherwise gives us value lower than ranges. Output of this subsystem was ranges and measured matrix, which every array represents each sensor values. In this section, I'm going to explain algorithms that I've used in this project. Vacuum cleaner robots use different algorithms. 3 of them are S-shape, wall follow, and a spiral. In this project, I chose S-shape and wall follow. And for doing that, I used Stateflow. Stateflow is a control logic tool used to model reactive systems via state machines and flowcharts within a Simulink model. We can create algorithms easily by creating flowcharts instead of writing 100 lines of code. I'm gonna explain a little about chart and how to add states and transition to your chart. In Stateflow, you can add states from here. After that, you have to add default transition to your state. You can create another state from here, or you can just right click on your state and drag to another place to make a copy of it. After that, you can create transition. You can write event name, condition, or action. In this project, I created S-shape and wall follow algorithms. In S-shape algorithm, robot move forward until it reaches to the wall. After that, it turns 90 degrees, where I added that to my algorithm by giving wheel right 1 and wheel left -1 for 0.22 seconds. And also, I added this feature that robot avoids obstacle and item in room and pass through them by changing its direction. In wall follow algorithm, robot keep its distance to the wall and try to remain beside walls and cleaning there. I use switch from dashboard in library to be able to change algorithm by switching it on and off and let one of them be S-shape and the other one be wall follow. And you can see if I click on S-shape, it turns to 0, and when I click on wall follow, it turns 1, and it changes between these two algorithms. In Stateflow, you should define each symbol or character you use in symbol pane. And if it was input, you should use input data, or if it was variable that only is in the chart, you have to choose local data. I used 2 local data in my chart. One of them was my counter local data that helped me in a shape algorithm to make difference between wall and item, and also using t as a local data as a elapsed time that I use in my wall follow algorithm. After t second, I defined t as a elapsed time. Now I'm gonna explain a little more about my algorithm. In S-shape algorithm, the robot moves forward until the front sensor sends something. If sends something, the robot check its counter. If it was odd, the robot acts like a wall to the obstacle and then came back. But if the counter was even, the robot changed its direction and passed through its obstacle until it reaches to another wall or another obstacle. In this subsystem, I prepared robot for moving in our 3D world based on my algorithms. In this subsystem, for right wheel and left wheel, I use transform sensors and get rotation matrix as an output, and with rotation matrix to VRML rotation block, I prepared wheels for 3D world. And for body, I used transform sensor to get rotation matrix and location of robot respect to the world. And like wheels, I used rotation matrix to VRML rotation block for rotational value, and for positions X, Y, and Z, I used matrix concatenate to make signal continuous, and use selector to make relation between system coordinates and 3D world coordinates. In Simulink, I used VRSync block, and I added file which was contained room and robot. Then in VRML3 or Virtual World 3, I chose rotation and translation of robot, rotation of right wheel, and rotation of left wheel. After that, I connected 3D interface output to VRSync block input, and now the model is ready for simulation. In this section, I'll run the model and see how algorithms work in my 3D room. And also I check the position of sensor after the simulation. I chose 35 seconds for stop time for this video. Also I raised view speed to see the result faster than usual. So I click on run. As you can see, with state flow, we can see what happens in every second in simulation. As you can see, the robot sends the wall and turns back again and move like a S shape. Again sends the wall. This time the robot sends the bit and again repeats its algorithms. that's enough for seeing that the algorithms were worked fine. So now I'm gonna go in sensor subsystem. I'm gonna see the position of right and front sensor. I click on scope. As you can see, the yellow line, which represents right sensor, has higher position value than orange line, which represents front sensor. And you can see that when robot move in 3D world and changes direction and turning 90 degree to left or right, the sensor positions remains accurate respect to each other. After we saw the results of S-shape algorithm, now I'm gonna click on wall follow and then click on run. As you can see, the robot keep its distance to the wall and cleans the area. In a state flow, we can see every states and every conditions besides our animation. After that, I'm gonna see the position of right sensor and front sensor. We'll see that their position are correct, like the previous algorithm. In this project, we learn how to import 3D model to MATLAB. We learn what is Simscape and the block that I used in my project. We learn virtual sensors. We learn two different algorithms that most vacuum cleaner robots use. And at the end, we saw the animation of robots' movement in virtual room. And also, we saw that algorithms worked fine. Thank you for your time.